So we're looking at the integral from 1 to 4 of 4x dx. And so first off, this is asking us for the area underneath the curve, or the area between the curve 4x and the x-axis from x equals 1 to x equals 4. So we did this last time, but I'm going to draw a real quick sketch here. That's not 4x. That's close enough. Pretend that goes to the origin. Look, it goes to the origin now. Here's 1 and here's 4. And so we're looking for this area underneath the curve. And as I mentioned last time, we're just going to do this using a right rectangular approximation method. And then we're going to shrink these intervals down, or make the number of intervals equal to infinity. And so every time we do one of these with a limit, which we're not always going to do them with limits, we're going to learn some rules to make it easier. But it's a limit as n approaches infinity of the sum from k equals 1 to n of the function at x sub k times delta x. It's always f of x sub k times delta x. Everybody good with that? Okay. And our delta x value is always equal to b minus a over n, or in this case, 4 minus 1 over n, which is 3 over n. So that is always the case. Delta x is always b minus a over n. I think I mentioned that yesterday. Did we talk about, did I talk about what x sub k is always equal to, or no? I don't think we talked about that. I think we just figured out what x sub k was. So let's just figure out what x sub k is. Well, in order to find whatever this height that I've just drawn horribly in blue is, it's the value of the function at there, right, at x sub 1. True? And how far over have I gone from the origin to get to x sub 1?
One plus delta x.
I should have gone over 1 plus delta x, right? X sub 1 is equal to 1 plus delta x, right? Delta x is the width of the rectangle, and I went over 1 unit before I got there. So what about x sub 2? It ought to be equal to 1 plus delta x plus another delta x, right? So 2 delta x. And so what should x sub k equal? It should equal 1 plus k delta x. And we'll note that no matter where I start there, right, whatever my lower limit is, that's the value that's going to go in here as the 1 plus, or it might be, if it was 2 to 4, it'd be a 2 plus, or if it was 0 to 4, it'd be 0 plus, which is kind of what we did here, right? In this one, our x sub k ended up just being 0 plus 2k over n. Well, now it's going to be 1 plus. It's always that a value. So we're going to say that x sub k is always equal to a plus k delta x 100% of the time. And our delta x was 3 over n. So our x sub k for this particular problem is 1 plus 3k over n. Good or no? Hopefully that's all right. So this now becomes a limit as n approaches infinity of a sum from k equals 1 to n of 4x sub k. So 4 times 1 plus 3k over n times delta x, which is 3 over n. Everybody good there? Okay. so let's distribute all this through. So I'm going to have a 4 and a 3n that I'm multiplying by all of this. So that's 12 over n times 1, which ought to be 12 over n. And then I'm going to have the 12 over n times 3k over n. That ought to be 60k, 60, I keep saying 60, 36k over n squared. Everybody agree with that? And then now we need to find the sum. So I'm going to break this summation down into two different pieces. One for k equals 1 to n of 12 over n. And then another one for k equals 1 to n of 36k over n squared. So first off, what can you tell me about 12 over n? What is it? It's just a
Constant.
It's just a constant. And so I'm adding 12 over n plus 12 over n plus 12 over n plus 12 over n. How many times for this summation? From 1 to how many times? Ought to be n times. And so if I add 12 over n times, that ought to be 12 over n times n, shouldn't it be?
Yes.
Okay. And then what about over here? The 36 over n squared is a constant, but the k is not. And we should know from yesterday, what's the sum from k equals 1 to n of k? That's the formula that I told you guys you should know and memorize. It ought to be n times n plus 1 all over 2. Good or no?
Good.
Okay. And what's the limit as n approaches infinity of 12n over n? Well, the n's ought to cancel. So that ought to just be 12. And then this one is just a rational function. And every time we do this, the degree of the numerator is going to be equal to the degree of the denominator, if we've done it correctly. And so that's a 36n squared over a 2n squared, which gives us what?
18.
And our final answer should be 30. Any questions or issues with that? All right. Let's do another one. You guys want to do this one on your own, or should I work through this one with you?
I don't know what everyone else thinks, but working with it or working with us through it would probably be helpful.
All right, yeah, sure, that's fine. Let's do one more and then I'll let you guys do the next one. So every time we're looking at one of these integrals, it's an integral from 0 to 3 of 2x plus 2. It becomes the limit as n approaches infinity of the sum from k equals 1 to n, always. And then it's f of x sub k, so 2x sub k plus 2 times delta x. And that doesn't change. All that changes is what the function is, right? But we take that function and we just replace the x with x sub k. Good or no?
Good.
Okay. And our delta x is always equal to b minus a over n, or in this case, 3 over n. And our x sub k is now always equal to a plus k times delta x, or just 3k over n. Good or no?
Good.
All right. So we then plug all that in. A limit is n approaches infinity. A sum from k equals 1 to n of 2 times x sub k, which is 3k over n, plus another 2 times 3 over n. Any issues or no?
Nope.
All right, cool. So now we just try to distribute all this through. This 2 times the 3k over n is 6k over n. And if we multiply that by 3 over n, what does that become? That would become 18k over n squared. And then plus 6 over n. Good or no?
Makes sense.
Okay. And then now we'll do the summation part. So 18k over n squared, the 18 over n squared is a constant. And the k is n times n plus 1 over 2. And then the 6 over n, if I add together n of those, just becomes 6n over n. Everybody good or no?
Good.
Yeah. And this is 18n squared plus some other less significant stuff over 2n squared. The n squareds cancel and you end up with 9, right? And then the 6n over n just becomes 6. And we should get 15. Everybody good there or no?
Good.
All right.
Wait, doesn't the I'm confused about because when you're doing n times n plus 1, isn't that n squared plus n? So then like I'm why can we cancel it if there's like an n squared plus n in the numerator and a
So,
in the denominator?
so let's write it out over here. It's 18n squared plus 18n over 2n squared, right? Well, it's just a rational function, isn't it? And we're looking for the horizontal asymptote of that rational function. And so we can either actually find this limit, like explicitly, or we can say, well, we know that the horizontal asymptote of a rational function, if the degree of the numerator and denominator is the same as just the division of the leading coefficients. But alternatively, if we plug in infinity, this becomes infinity over infinity, right?
Oh yeah.
So using L'Hopital's rule, it's a limit as n approaches infinity of 36n plus 18 over 4n, which is still infinity over infinity. But using L'Hopital's rule, that becomes the limit as n approaches infinity of 36 over 4, which is just 9. So it's just one of the ways that we evaluated limits before. Alternatively, we could have divided everything by n squared. Remember when we did that? We divided all of these by n squared. And then the n squareds cancel, and you end up with 18 plus 18 over n over 2. And as n goes to infinity, that goes to 0. Since you just have the 18 over 2. So a couple different ways to do it. But does that make sense?
Yeah, thanks.
Any other questions on this problem?
How did you go from 6 over n to 6n over n?
Okay, so let me put another page in here. So I'm summing together a bunch of 6 over n's. Right, that's what this is saying. The sum from k equals 1 to n of 6 over n is 6 over n plus 6 over n plus 6 over n, as many times as until we get to n. So we're going to do that n times. And so if I have n 6 over n's added together. Well, that's 6 over n times n.
All right, thank you.
Any other questions on that? All right, let's see if you guys can work through this one on your own. I'll give you 3 or 4 minutes to try and do this one. Ready, go. So, first off, what was your delta x value? Should have been 4 minus 2 over n, or 2 over n. And your x sub k value ought to have been 2 plus 2k over n. Everybody good with that? Any issues or problems with that?
No.
All right, spectacular. So this should have become a limit as n approaches infinity of a sum from k equals 1 to n of 3 minus 2 times x sub k, which is 2 plus 2k over n, times delta x, or 2 over n. Good?
Yep.
All right, perfect. So then we'll distribute all that through. The 3 minus the 4 that we get is negative 1 times the 2n. So that's a negative 2 over n. And then a negative 2 times the 2k over n is negative 4k over n, times the 2 over n is negative 8k over n squared. Everybody agree with that?
Yes.
All right, good. And then now we do the summation. A limit as n approaches infinity. The negative 2 over n just becomes negative 2n over n. And this becomes negative 8n times n plus 1 over 2n squared. The first one is negative 2, and the second one is minus 4, so we get negative 6. Everybody good there, or no? All right, I assume we're good. So all the ones we've done so far were just linear functions. We could use geometry to find all of these values. And you may be wondering, how did we come up with a value that was negative 6? Well, the reason we came up with a value that was negative 6 is because part of this function lies below the x-axis. And there's going to be a distinction between when a function's above the x-axis and when it's below the x-axis in terms of area and integrals. And we're going to talk more about this later on, but I just want to touch on it briefly now. If a function is above the x-axis on the interval on which you're looking for the integral, then that means the integral will be positive. If the function is below the x-axis on the interval, it means that the integral will be negative. Now, that does not necessarily mean that we would call the area negative, because area can never be negative. So if we talked about the area between a function and the x-axis, it's always positive, but if the function is below the x-axis on that interval, the integral itself will come out to be a negative number. And we would just then take the opposite of it to know what the actual area is. And if the function crosses through the x-axis on whatever interval we're looking at the integral on, then we have to do a little extra work, but we'll talk about that another day. Does that sort of make sense as to why we might get a negative value? Hopefully. Okay. So let's do another one. This one is a quadratic function. So this one we wouldn't be able to use our regular normal geometric formulas, for a trapezoid or a triangle to find the area underneath this curve, the only way for us to find the exact area underneath this curve is by using the actual integral. So we'll do one of these together, then I'll have you do one on your own with the quadratic, and then we're going to sort of move on to some other stuff. But we should have plenty of time for it today. So nothing changes at the beginning. This still becomes a limit as n approaches infinity, and it's still a sum from k equals 1 to n, and it's still f of x sub k times delta x. And what's delta x? Ought to be 2 over n. And what is x sub k? It ought to be 0 plus 2k over n. Everybody good with those values? And so f of x sub k is 3 times x sub k squared. And then delta x is 2 over n. Not getting a lot of response out there. Are we all right with that or no?
Yes.
All right, cool. So now multiply it all together. 2k over n squared in the numerator gives us 4k squared. All right, so 4k squared times 2 is 8k squared times 3 is 24k squared. So we've got a limit as n approaches infinity of 24k squared over the n squared from this times another n is an n cubed. Is everybody good there?
Wait, did we need the sum in there or did you already do that?
Oh, sorry, I forgot to write my sum.
Oh, okay. Okay.
Yeah, I
just
have
making
a
sure I
bad
didn't miss
doing
it.
that. It's like when I have a limit, half the time I forget to write my limit. Well, when I have a summation, half the time I forget to write my summation. And when I have both of them, half the time I'll forget the second one. I always remember the first one, but then I get involved in it and forget the second one. Thank you for mentioning that. All right. I believe yesterday we talked about what the summation of just k squared was. Anybody remember what that was?
It was
Was it like
n plus 1 times 2n plus 1 over 6.
N times n plus 1 times 2n plus 1 over 6. So everything else in there is a constant. It can stay. Now we'll do the summation part, and I won't have to keep writing it. The limit as n approaches infinity of 24 over n cubed times n plus 1 times 2n plus 1 all over 6. And still, even with the quadratic that we started with, the degree of the numerator and the degree of the denominator are still going to come out to be the same. And so in the numerator, we've got what? We've got a 48 n cubed plus some other junk that's not as significant, divided by a 6 n cubed. And we can just divide the leading coefficients to get 48 over 6, which is 8. Everybody good with that?
Wait, so will we ever have to like use like this method to find like integrals of like cubic functions? Since I guess we'd have to know the summation like formula for cubic stuff too.
Yeah, you do not need to know that, and no, you won't have to do it for anything higher than a quadratic with this method. Now, for the rules that we're going to learn next week, yeah, you're going to have to be able to do it with a cubic and a 4th degree, and then a sine function, and an e to the x function, and a log base 2 of x function. Well, not a log base 2 of x function, but a bunch of other functions. So short answer, no, you don't need to know it for cubics. All right, last one of these. You guys try and do this one on your own. I'll give you 2 or 3 minutes. The algebra might get a little bit messy, but you should be all right. So take about 3 minutes and work on this one. Our delta x value should have just been 1 over n, 2 minus 1 over n. Right? And our x sub k ought to be 1 plus k over n. Everybody good with that?
Yes.
So we end up with a limit as n approaches infinity of a sum from k equals 1 to n of 1 minus 6 times x sub k. In fact, you know, we're gonna square this 1 plus k over n. So I'm just gonna do that now. 1 plus 2k over n plus k squared over n squared times our delta x. Everybody good with that?
Yep.
All right, and we got a limit then as n approaches infinity. The sum, I'm not going to forget my sum this time, from k equals 1 to n. Here we have 1 minus 6, so that's negative 5. And then times the 1 over n is negative 5 over n. And then a negative 6 times a 2k over n is negative 12k over n times the other 1 over n, so minus 12k over n squared. And then minus 6k squared over n cubed. Everybody good with that?
Yeah.
All right, cool. And then as we do our summations, the negative 5 over n ought to just become what? Negative 5n over n. And the we get 12 times n plus 1 over 2n squared. And then minus 6 times n plus 1 times 2n plus 1 over 6n cubed. Everybody good with all of those? And our first one becomes negative 5. Our second one becomes negative 6. And our last one becomes negative 2. Everybody good there or no? Any questions, any issues? We all good?
Good.
All right, perfect. Cool. So this evening, you'll have an assignment with some of these to work through. And then I'm going to give you guys another short assignment to do sometime over the weekend, which is about something called the trapezoidal rule, which is just another way. I meant to do it when we were doing the rectangular approximations, but I forgot. It's just another way for us to approximate the value of the area underneath the curve. And the trapezoidal rule is, rather than using rectangles, we use trapezoids. And it's more accurate than the midpoint rectangular approximation, which is the one that was the most accurate of what we were doing before. So the trapezoidal rule, and we're just going to go through it real quick and do one. Shouldn't be too bad. Trapezoidal rule just comes from making a bunch of trapezoids. So rather than doing rectangles, and sometimes these are a little bit of a mess here. When it crosses through the x-axis, it ends up being 2 triangles rather than trapezoid, but that's okay. Wow, those last couple weren't very good. But we'll notice that we just get a bunch of little trapezoids, right? If we connect the heights of our function at each beginning and end point of our subintervals. You can see we're leaving a lot off of there. And we're leaving a lot less off of there than we were with the rectangular approximations, or we're going over by less, or we're going under by less. And so what's the area of a trapezoid? Should be base 1 plus base 2 divided by 2 times the height. So what are each of those things within our function? Well, the height of each trapezoid is just that's h right there, right? It's just the length of the subinterval. That's the height of the trapezoid. And then base 1 and base 2 are just these are the y values of the function. Everybody see that? So they're trapezoids that are turned on their side. They're not actually sitting on one of their bases. Everybody good there now? Yes, no, maybe?
That makes sense.
Okay, cool. So the formula to find this area approximation would then just be the first value at y plus the second value at y, those are your two bases, divided by 2 times the height. And then the next one would be y1 and y2 divided by 2 times the height. And the next one would be y2 and y3 divided by 2 times the height, and so on all the way till the last trapezoid. And this is exactly what you'll have to do if you are given unequal subintervals. If the intervals are not equal, as in h1 might be different than h2, which would be different than h sub n, like each of those subintervals is different than the other ones, then you have to find each height separately. And then you have to find the y values of the function at the end and the beginning, and the end points of that interval, and divide them by 2. And this will often occur if you're given a chart of values, just a chart of values, or just a graph with some data points plotted, but no actual function given to you. If you're given an actual function, you know, f of x equals x cubed or something, you should be able to divide it into equal subintervals if you want to. Okay. So if the subintervals were equal, what does each of these have in common?
The height?
Right, the height is always the same, and they're all being divided by 2, right? So we could make this h over 2 times y naught plus y1 plus another y1 plus y2. Right, there's y naught, there's y1. Y2 would come from the second trapezoid, but then we'd also have another y2 from the trapezoid after that, and we'd have each y1 and y2 and y3 and y4 all the way up to the very last one. We'd have 2 of each of them, right? But only the first one and the last one would be used in one trapezoid. So if we had equal subintervals, we could rewrite this formula as h over 2 times y naught plus 2y1 plus 2y2 plus dot 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 2y sub n minus 1 plus just 1 y sub n. Okay. And that would mean that our h value was equal to b minus a over n, right? The length of the interval divided by the number of subintervals. Good or no?
Good.
Cool. And so one other quick thing to note is that this is equivalent to finding the average of a right and a left endpoint rectangular approximation. And one more quick thing that we should note about this also is that if a function is concave down, a trapezoidal approximation is going to be underneath this, right? So if the function is concave down, this should be an underestimate. And if a function is concave up, should have used a different color here, but then, oh, that was really bad. It should be a slight overestimate. So you want to note that. Good, or yeah, somebody unmuted for half a second. Everyone's good?
Yeah.
Okay, cool. All right, so we're going to real quickly, we're going to use the trapezoidal rule with n equals 4 to estimate the integral from 1 to 2 of x squared dx. And what do we know about the function x squared? Is it concave up or concave down?
Concave up.
It's concave up. So if our function is concave up, we should be getting an overestimate, right? So we'll just note that off to the side. So first off, n equals 4 means 4 subintervals. Good or no? What's b minus a over n? What's h equal to? 2 minus 1 over 4. So our formula should be 1/4 divided by 2 times our first y value. So what are our, if we're dividing 1 to 2 up into subintervals that are equal, they each ought to be a fourth long. So 1 to 5/4, 5/4 to 3/2, 3/2 to 7/4, and 7/4 to 2. Good? So
Yes.
what's the first y value? It should be 1 plugged into this function, so 1 squared. And the next y value, which gets multiplied by 2, is 5/4 squared. And then 2 times 3/2 squared, 2 times 7/4 squared, and then just 2 squared at the end. Everybody good? 1/8 times 1 plus, let's see, what is this? This is 25/16 times 2, which is 25/8. This is 9/4 times 2, which is 9/2. This is 49/16 times 2, which is 49/8, and then that's a 4 at the end. Common denominator should be 8. Right, so this one's going to become 36. We got 25 plus 36 plus 49 plus 8 plus 32. So what does that become? 150 eighths, and then times 1/8, 150 over 16, or 75 eighths. Hopefully I did that arithmetic right. Does that arithmetic look right to everybody?
Shouldn't it be 64 for the denominator?
Oh, yeah, 64. I added those together, didn't I? That was stupid of me. Thank you. $64. 32. Yeah, it still doesn't reduce. That's better. Ah, yeah. It's been a long day. Arithmetic's hard now, apparently. All right. Any questions on the trapezoidal rule there?